Welcome to this video of Module 4 on Auto-Configuration. In this module, we'll be talking about IPv6 related protocols. We'll address the following topics: ICMP version 6, Path MTU discovery, Neighbor discovery protocol, multicast listener discovery, and auto-configuration. Introduction. The IPv6 scenario has several differences compared to IPv4. First, as we saw when discussing addressing, there are no more broadcast addresses. Instead, well-known multicast addresses are used to replace them. ARP, the Address Resolution Protocol, used to find out the Layer 2 address corresponding to an IPv4 address, also disappears. Under IPv6, this function is provided by the Neighbor Discovery Protocol. Likewise, IPv6 makes extensive use of ICMP version 6, which is used by several protocols needed for the proper operation of IPv6, such as the Neighbor Discovery Protocol, Multicast Listener Discovery, and Path MTU discovery. Other protocols also use ICMP-v6, including Mobile IPv6, which offers a mobility service at the network level. We'll now describe the protocols needed for IPv6. ICMP-v6. As already mentioned, ICMP-v6 messages are critical for IPv6, as they are used in several protocols needed for the proper operation of IPv6. This is why it is important to be careful when filtering ICMP-v6. The incorrect filtering of ICMP-v6 will make it impossible to send or receive data over IPv6. ICMP-v6 messages can be classified into two categories: error messages with type values ranging from 0 to 127, and information messages such as echo request and echo reply, which are used for diagnostic purposes. An ICMP-v6 packet consists of a type field and a code field, each of which uses 8 bits. There's also a 16-bit checksum field. These are followed by the rest of the message. There are 4 types of ICMP-v6 error messages: destination unreachable, packet too big, time exceeded, and parameter problem. The code specifies the cause of the error, which can be quite useful when troubleshooting. Path MTU discovery. MTU, or Maximum Transmission Unit, is an important concept. It is the size in bytes of the largest packet that can be transmitted. Link MTU is the packet's maximum length in bytes, and Path MTU is the smallest MTU of any of the IP hops from a source to a destination. In IPv6, Link MTU has to be at least 1280 bytes, while in IPv4, it had to be at least 68 bytes. The link layer must find a way to offer this 1284 byte MTU. MTUs are important for IPv6 because the fragmentation process changes, as we will see later, and the use of encapsulation is more frequent, so the available MTU is reduced. Path MTU discovery for IPv6 determines how to proactively discover the path MTU between a source and a destination by sending packets larger than 1280 bytes, beginning with the first hop's MTU. Let's see how this path MTU discovery process works. Even if not used proactively, it will be used by IPv6 to detect potential MTU problems and use fragmentation, which is different in IPv6 and IPv4. In IPv4, packets are fragmented along their path. Any router can fragment a packet and send the fragments to their destination. Instead, in IPv6, packets can only be fragmented at the source. Let's suppose a source sends a 1500 byte packet to a destination. This packet will hop from one router to another until reaching router B, where it finds a 1400 byte MTU. This means that the packet does not fit in the link. Router B discards the packet and sends an IPv6 packet to big message, including the information on the 1400 byte MTU that generated the error. Once it receives this packet, the source will fragment the original packet using the fragmentation extension header and generating smaller packets that will be able to traverse the 1400 byte MTU. Care must be taken when filtering IPv6. If the IPv6 packet that specifies the error doesn't reach the source, the data will not be transmitted. The Neighbor Discovery Protocol uses 5 IPv6 messages: Neighbor Solicitation, Neighbor Advertisement, Router Solicitation, Router Advertisement, and Redirect. The redirect message is used in IPv4 and therefore requires the same level of attention. NDP provides several services on a LAN: discovery of available routers, discovery network prefixes, and configuration of network parameters. It also provides auto-configuration of network parameters, the equivalent to ARP in IPv4, address resolution for mapping between IPv6 addresses and link layer addresses, duplicate address detection to check whether an IPv6 address is already in use, or neighbor unreachability detection to proactively check whether a neighbor is still reachable on the LAN and refresh the information, including the link layer address. Neighbor Discovery Protocol (NDP) is used in host-to-host communications through neighbor solicitation, neighbor advertisement messages, and router-to-host communications through router solicitation, router advertisement messages, always within a LAN or a local network. A host will send a neighbor solicitation message in two cases: to query a MAC address or to check the reachability of a neighbor. A host will also send a neighbor advertisement message in two cases: in response to a neighbor solicitation message or to quickly propagate new, unsolicited information. A host will send a router solicitation message when setting up an interface, and a router will send a router advertisement message in response to a router solicitation message or periodically to report network parameters. Multicast Listener Discovery. Multicast Listener Discovery, or MLD, is another component of the IPv6 suite. It is used by IPv6 routers for discovering multicast listeners on a LAN. Much like IGMP is used in IPv4, there are two versions of MLD: MLD version 1 and MLD version 2. There are three types of MLD messages: multicast listener query, sent by a router to discover what multicast groups the hosts are listening to; multicast listener report, sent in response to an MLD multicast listener query, although an unsolicited report message can be sent by a host when it begins to listen to a multicast group. For example, all hosts FF02:1 multicast listener done, sent by a host when it stops listening to a multicast address. This protocol is also used by all IPv6 nodes because they listen to well-known multicast addresses, such as all hosts or all routers. So they will send report messages specifying when they are listening to these multicast groups. Auto-configuration. There are two options for considering a host network parameters: manual or auto-configuration. Auto-configuration is the process whereby network parameters are configured automatically. In IPv4, the only auto-configuration option was DHCP. Instead, IPv6 allows more options, which we'll now describe. There are two types of scenarios, with or without a router. If there's a router, it will send route advertisements containing flags M and O. These two flags allow for up to 4 combinations. Hosts must look at the M and O flags and then configure themselves automatically. Flag M provides information on how to configure the IPv6 address. Flag O provides information on other parameters, for example, the DNS. In the scenario without a router, DHCP v6 may be used to configure the IPv6 address and DNS server. So we have two tools: stateless auto-configuration or SLAC, when flags M or O are set to 0, and stateful auto-configuration or DHCP v6 when the flag's value is set to 1. There are 4 possible combinations of flags M and O. Therefore, the following possibilities can be used: SLAC to configure IP addresses and other parameters, or SLAC for the IP addresses and DHCP v6 for other parameters, in this case known as stateless DHCP v6, or DHCP v6 to configure the IP address and SLAC for other parameters, or DHCP v6 to configure both the IP address and the other parameters. Thank you for your attention. We've just watched a video on IPv6 related protocols. In the next video, we will talk about stateless auto-configuration.